Okay, so to wrap up section 15.1, we have a brief summary here. Wait a minute. Oh yeah, I just didn't choose it. So it said the domain of a function in several variables of n variables is a set of n tuples, a1 to an and rn, for which f of a1 to an is defined. The range is a set of values taken by f. So the domain are all the possible inputs that we can have for our function, and then the range is going to be our possible outputs. And so we're extending notions beyond the 3 space and putting it in the general space, which is Rn. Okay, so we're generalizing notions that we know about 2 space, 3 space to the n space. So now we're going to begin with section 15.2. Limits and continuity in several variables. Okay, so in this section, it develops limits and continuity in the multivariable setting. We focus on functions of 2 variables, but similar definitions and results apply to functions of 3 or more variables. Let me see. We focus on functions of 2 variables, but similar definitions and results apply to functions of 3 or more variables. Okay, so we're using functions in 2 variables to get a sense of 3 variables and more. Recall that on the real number line, a number x is close to a if the distance between x minus a, the absolute value, the distance absolute value of x minus a is small. So, those 2 points are close if that distance is small. So then in the plane, a point x comma y is close to another point, a comma b, if the distance between those 2 points, again using the distance formula, root x minus a squared plus y minus b squared between them is small. So in a plane, again, these 2 points are close if the distance between those two points are close. So note that if we take all the points that are a distance of less than r from P, as in figure 1, okay, this is a disk. The disk with centered at P of radius r. So again, centered at P, that does not include its boundary. If we insist also that the distance between x and y and a and b, between these 2 points, is not 0, so they're not the same point, then we get a punctured disk that does not include P, and that we denote as d star of P and R. So now assume that we have some function of x and y is defined near some point P. So we have a function that's defined near a point P, but not necessarily at P itself. In other words, so we have f of x, y is defined for all x comma y in some punctured disk, d star, centered at P with radius r, again with r being positive. We say that f of x, y approaches the limit L as the point x comma y approaches P. Where's the x comma y? So x comma y, you see on the disk on the left, it's just a point that fits this definition of being closer to P than R, or within the range of R. Let's look at that. So if we insist that the distance between x, y, and a and b, where's a, b? AB is not 0. Is that for our P? Yeah, so A, B are the coordinates of our point P. Okay, A comma B. So we insist that, sorry, I keep reading the same question, same sentence over and over. Okay, if we insist that the distance between our x and y and our point P is not 0, so the x and y is not directly on our point P, then we get a disk that does not include P, and we denote it as d star. Centered is a d star, the disk centered at P with the radius r. So now assume that this function f of x comma y is defined near the point P. So we have some f of x defined near P, but not necessarily at P itself. So in other words, f of x, y is defined for all x and y in some punctured disk centered at P with radius r, again with r being positive. We say that f of x, y approaches the limit as x comma y approaches P if the distance between f of x, y minus the limit becomes arbitrarily small for some x, y. So the function evaluated at x comma y minus the limit is arbitrarily small for some x comma y, sufficiently close to p. 2c, figure 2c in this case. Doesn't like I have that one right now. It's probably further down. Okay. So we have the function is centered, the disk is centered at the point P, which is a comma b, and we're observing some x comma y, some arbitrary x comma y that's within this disk of radius r, close to our point P. Okay. So then we say x comma y is close to the point P if f of x comma y minus the limit, the absolute value is less than some epsilon. So what epsilon is, so this is an introduction to the epsilon definition for limit. But epsilon is you got to think that it's a really like a really small unit. So you know it's going to be really small, but it's not zero. So it's just really small, but it's not zero. And so we say that our point x comma y is closer to our point P if it's within some epsilon distance between P and the radius of r. Let's kind of go back and look at some more. 63. Did I go out of order? 62. Oh, this needs to go up. I thought that looked a little strange. I think that this goes here. That's 763. So that's a summary for 15.1. And then, so that's 763. This should be 64. 65 and 66. 15.2. Sample 1. 763. This should be 64. 68. 69. Okay, I think the order's fine though. Okay. So again, let's kind of recap this notion. So we assume that some function is defined near P, but not necessarily at P itself. In other words, this function is defined for all x comma y in some disk centered at P. We say that f of x approaches the limit L as x approaches P if the distance between our function value and our limit is arbitrarily small for some arbitrary point. Okay, in this case, we say that the limit as our point x comma y approaches P, so as our point that we're considering approaches P, then our function value is going to be, this is the same as the limit as xy approaches our point P, which is a comma b, of our function value is going to be equal to some L. So then the definition, assume that the function is defined near a point P, then the limit as our point approaches the center of our function is going to be L. If for some very tiny positive epsilon, there's a delta such that if our point x comma y satisfies, so it's the distance between our point and our center is between 0 and delta, then the distance between our function and our limit is less than epsilon. Yeah, this is an epsilon delta definition for limit. We're going to continue this momentarily.